Good morning, I'm Timothy Purcell, and I want to do a linear programming problem for my Math 1324 class. I'm going to do this one using the graphical method. Here's the problem. Oh, and by the way, for the students enrolled in my classes right now, it looks like this is like your number 6 from homework 10. So this should be very similar to your problem number 6. Maximize and minimize. The objective function is p equals 12x minus 18y, subject to the constraints 4x plus 5y is less than or equal to 30, 4x plus 3y is less than or equal to 20, x is bounded between 0 and 5 inclusive, and y is bounded between 0 and 8 inclusive. I think I'm going to first of all address these last two inequalities, the ones involving x and y. For linear programming, the process to work, we know that we have to have non-negativity constraints, and at first glance you might think we don't have those constraints, but yes we do. That's what the left side of these last two inequalities are saying. X is greater than or equal to 0, y is greater than or equal to 0. So that's saying our graph will just be in quadrant 1. The inequality involving x, I'm going to deal with that one first. X less than or equal to 5. We have to graph the boundary line x equals 5. So here's my not my scratch paper, here's my graph paper. There, right here. I'm going to, we have to graph the line x equals 5. If your linear equation has an x and no y, we know that that's a vertical line passing through 5 on the x-axis. So that's a vertical line. So let's see, 1, 2, 3, 4, 5. Right there. It's a vertical line passing through 5. Okay. I'll put it, by the way, I'll put arrowheads on there. Okay. Next, and think about this inequality. Where are the x values less than or equal to 5? Well, that'd be to the left out here. So I've just now shaded between the y-axis and the x-axis in the first, the pink line in the first quadrant. So at this point, I have that little unbounded region shaded. Now I'm going to address y less than or equal to 8. Okay, y less than or equal to 8. That means we have to graph the line y equals 8. Y equals 8, you'll remember from your algebra classes, if the linear equation contains a y and no x, that's a horizontal line. So this is a horizontal line passing through the y-axis at the number 8. So here we are, 1, 2, 3, 4, 5, 6. There's the horizontal line. That might be helpful to make a note that that's the number 5 on the x-axis, that's the number 8 on the y-axis. We want to shade the region where y is less than or equal to 8. Well, all these points up here above that horizontal line have y values bigger than 8, so we'd shade below it. As a result, the region that's been shaded both times is this rectangle right there. Very nice, feasible region, but we're not finished. Now we have to deal with 4x plus 5y is less than or equal to 30. So we have to graph the boundary line. 4x plus 5y is equal to 30. Finding our intercepts. When x is 0, y is 6. When y is 0, x would be 30 over 4. That's the same thing as 15 halves, 7 1/2. So, and I suppose some people might want to write this line in slope-intercept form and use raise over run to draw the graph the line. But so often the intercepts are corner points to the feasible region that it's just more sensible to find the intercepts to draw the line, because more than likely you'll need to know those intercepts anyway. So 0, 6, and 15 halves. So 1, 2, 3, right there, and 15 halves, that's 7 1/2, right there. There's 6, there's 7 1/2. I'll label it 15 halves. We draw our boundary line. Okay. Now, which side of this line are we going to shade? Are we going to shade, I guess depending on how you look at it, it's either to the right or above, or we're going to shade below. Here we'll test a point. Choose a point that's an ordered pair that's not on the green line, that slanted line I just drew, and test the inequality. The test point I like to use is the origin, okay? So because it's easy to plug in 0 for x and 0 for y. So testing 0, 0, 4 times, right, there, 4 times 0 plus 5 times 0 is less than or equal to 30. So 0 is less than or equal to 30. True or false? That's true. So we now shade the region below that green line. So at this point, this region up here on top is no longer shaded. That's no longer part of our feasible region. At this point, the region that's been shaded is this little quadrilateral right out here. This region wouldn't be included because it wasn't shaded for the x and y inequalities. That little triangle there is still unshaded. One more inequality. This is the inequality. 4x plus 3y is less than or equal to 20. We have to graph the line 4x plus 3y is equal to 20. So we make ourselves a table of values. Plugging in 0 for x, we get 20/3. So what is that, 6 2/3? Then plugging in 0 for y, 20 divided by 4, we get 5. So plotting the line, let me see that there. We have, we said 20/3 is the same thing as 6 2/3. So we have 0, 6 2/3, that's just slightly above 6. And we have 5, 0. Oh, that's right there. Draw the boundary line. Now we have to decide. Here's that purple line, that slanted purple line that I just drew. Are we going to shade above it or below it? Are we going to shade to the right or to the left? And to decide, we'll test a point that's not on the line. I'll test 0, 0. So testing 0, 0. 4 times 0 plus 3 times 0 is less than or equal to 20. 0 is less than or equal to 20. That's a true statement. So we're going to shade the side that contains our test point 0, 0. So this little triangular wedge right here that was shaded, it's no longer shaded. Our feasible region is now this region right here. Let me draw it real dark. Let me shade it in. That's the region that was shaded 4 times. There. And now we need to find the corner points. So some of the corner points, we can read them off just from looking at the graph. that point right there, that corner point is the point 0.06. So we can read that one off without any trouble. So our corners 0.6. What else have we got as a corner point? We have, moving down the boundary lines, here we're at the origin, 0, 0. Move across, that point right there was 5, 0. So there's 3 of the corners. Now we only have 1 corner left, and let's see, moving along up here, it's that point right there. And it's formed by the purple slanted line and the green slanted line. So it's formed by, where is it? It's formed by 4x plus 5y equals 30 and 4x plus 3y equals 20. We need to know, where do those two lines intersect? 4x plus 5y equals 30 and 4x plus 3y equals 20. That's a system of equations. I'd use either elimination or substitution. I would use elimination. So let's see, I'm going to come here and I'm going to find that point of intersection. 4x plus 5y equals 30 and 4x plus 3y is equal to 20. Using elimination, you could say, okay, these x terms have the same coefficient. We want them to have the opposite signs, though, so I'll multiply the second one by -1. So we have 4x plus 5y equals 30. And now I have the negative of 4x minus 3y equals a -20. Add the two equations together. Add the two equations together. 4x minus 4x goes to 0. 5y minus 3y, that gives me a 2y equals 10. So y is equal to 5. Oh, well, let's see. So that y coordinate is 5. If you'll notice, it looks like my point of intersection is a little bit more than 5. Well, yeah, okay. That's why just looking at the graph is never that great an idea, unless it's things like on the points you've already found, like intercepts, where you know the coordinates already. But this point of intersection right there, the y coordinate is 5. So for my list of corners, I know that this last one, the one I'm looking for now, has a y coordinate of 5. I need to find the x coordinates. So I'll come back here. I know y is equal to 5. I'm going to plug y y equals 5 into one of these equations. It doesn't matter which one. So I'm going to use 4x plus 3y equals 20, just because the numbers are smaller. So 4x, 3 times y, we're taking that 5 and plugging it in there. 3 times 5, that's a 15. So that says 4x is equal to 5. So x is equal to 5/4. So I now know the y coordinate for that corner point is 5/4. So now I've found all of my corners. My last corner point that I was looking for was 5/4. Now, what's the function I wanted to, what's my objective function? Looking way back at the beginning, the thing we haven't even used yet so far, that objective function p equals 12x minus 18y. So p equals 12x minus 18y, p equals 12x minus 18y. And I can go through plugging in the numbers. First of all, plugging in 0 for x and 6 for y. I'm getting a negative. That's a 0 minus, that's a 108, so a negative 108. Plugging in 0, 0. That's a 12 times 0 minus an 18 times 0. That gives me just a 0. Plugging in a 5 0. 12 times 5 minus an 18 times, no, plug in a 5 0. Is that what I said? So I'm getting a 60. Last one, 5/4, 5, the point that we had to find using elimination. 12 times 5/4 minus 18 times 5. And let's see, 4 will go into 12 3 times, so that's a 15 minus a 90. 15 minus a 90, I'm getting a negative 75. When we look at our feasible region, we see that it's a closed bounded feasible region. For closed bounded feasible regions, both the maximum and a minimum value exists at a corner point. Since we have both a maximum and a minimum, since we have a closed bounded feasible region, we have both a maximum and a minimum value occurring. So the smallest of these p-values is the minimum, the largest is the maximum. So by my calculations, it looks like negative 108 is the minimum value of the function. I'll label that an min for minimum. And the largest one here, 60, that's the maximum. And let me see. I believe all that they're doing, all they want is just the maximum and the minimum values. So I'm going to write it down neatly. I'm going to say the maximum is 60. The minimum was negative 108 for my final answer. And let's see, if you choose any point, you can choose any point you want to in that feasible region or on the boundary lines, what have you. Any point in that feasible region, you will never get, a p-value bigger than 60. You'll never get a p-value smaller than negative 108. That's the significance of these answers that we found. For the points, any of the ordered pairs that are in that shaded region or on the boundary lines, when you plug them into the objective function, you'll never get a number bigger than 60. You'll never get a number smaller than negative 108. Okay. Oh, excuse me. Okay, well, I think I'll take a break now. So, bye-bye.